We start recording the thing. Okay. What am I doing? Yeah, no. It's okay, screen. Yes. So the first thing I want to emphasize is to talk about is the classroom that we are able to get more BA lab. So there's one more BA lab we need to secure. Once it's done, then the rest of semester except the fun exam will be all in the BA lab. So then we don't have to go all over up the hill, and that would be a little bit time consuming for every one of us. So this is the first thing. The second thing, of course, is the plan of the day, right? The plan today we will be finishing the lesson 4. I think we're almost done. Just some left over there. We will go over it. I did notice that the version I upload is not the latest, so I just revise it because it's a little bit more simplified compared to the last one. And we will talk about the I think it's the lesson 5. Okay, it's there already, but somehow I'm not opening. So so lesson just I guess I hope you have enjoyed the public holiday. I don't know whether you hike during this long holiday, but I did do some hike in Hong Kong Island, but there's some good hiking. I hope you enjoy. So let's us very quickly review what we have done in lesson 4. Okay, I mean the last class, right? The main idea is to look at two variables and look at how they're related, right? Because at the end of the day, we want to build how different variables related, right? Because that is the ideal data, right? Data is like we try to build up how variables or column of data, how they're related, or either using prediction or either used in explanation of causal impact. So the first thing to focus is on just simple two columns, X and Y, right? How X related to Y, right? And we learned there are several ways to do it, right? The most basic thing, right, is to focus on the idea, what we call the group thing up is called the basic thing is called the bin scatter plot, right? Just group them into multiple groups and look at the group mean with a prediction, right? Suppose we want to remember the hotel data. We don't want to use the distance from the city center to predict the price, right? And of course, the closer they're more expensive. And then the way we do it is look at how close they are, right? And the closeness is group them into the case where the distance to the city center is less than 2 miles or not, right? If less than 2 miles, and group them to close. More than 2 miles is far, right? And then look at the average of the close is 1.5, right? That is our model, right? This is the simple as we want, right? Because if you don't have this, right, average of the price will be your model, right? There's nothing used. The most simplest is to divide them into two groups, right? And then we know that how to do it when we have more than 2, we have 4, and then X many ask why you have to do this particular grouping. No, there's no need to use this 1, 2, 3 as cutoff point. You can do whatever cutoff point you feel is reasonable, right? And then what is the reasonable one? Probably, I don't know. I have no good idea what is good, right? But you do note that there, when you have 4 groups, it's more looks like this, right? And you will probably ask what is the good way. This is the way to do, but we do have another way we call the lowest, right? And this is the way that you can thought in this way, right? And obviously, right, you put a point cut at 2 and 3 is a good, you could put a horizontal line there, right? 2 and 3 and 3 to 6 is a good horizontal line here, right? And here maybe fitting any horizontal line doesn't work well. Right? Maybe it's okay. Maybe you can group them here, right? Maybe you want to make this into a much finer partition, right? But that is if you want nonlinear, this is the best model you can get, right? And if you just simply look at distance, right? And obviously, this is the worst deal you can get, right? And you don't want to take this one, right? Must be, if you want to take this one, must be some reason other than distance, right? That would justify your choice. And if you simply look at distance, right? And these all are good choices, right? That would be, I mean, as economics said, hold other thing constant, right? If other things are similar, then you want to pick this, right? And which one to pick, probably look at other dimension of the factor we haven't considered in this diagram. But and we'll talk about multiple regression today, but we now focus on only single variable explanation. And we explain one of the main tools that we use for this class, as well as the it's called the regression method, right? Which is the simplest one is looking at scatter plot. You choose the intercept and the slope, right? You want to minimize the vertical distance. The reason that we focus on vertical distance is because that is our prediction error, or as the variation that we want to explain, right? And that is the part that the distance is the part that that thing is not explained by the model, right? We want to figure out that to minimize this prediction mistake, right? And later you will see this is what we call the SSE, right? This guy is actually SSE, and this is later you will see this is the way that the average of this is called MSE, and then all the when you compare machine learning models, computer regression models, that is the criteria that we use to figure out which model that minimizes the best. Okay, and of course, here is linear. We have alpha and beta, but do note that this guy, right? This is what? This is the line that you're trying to choose, right? So this is what we call the yi hat, right? Is the model, right? So that's why this is the guy we use this for evaluate how good your model fit, right? This is the model predict this guy. This is the actual value the data is, and then you want this. If it's identical, then your model is perfect, right? But in general, they're not the same, right? And that sum up will be a big number. And what we want is to minimize, usually you minimize over n, right? This is SSE, and you minus n is the MSE, right? Minus n or minus 2 depends on the model you have. But anyway, this is the thing we care. And then usually sometimes you took the square root that become our MSE, but we'll be more clear when we look at the models. Okay. And we tell you how, in particular, if you use calculus tools, how you have the alphas and betas. I don't think it's a big concern for us, but I just leave the formula here because you can see the book, right? Because there's simply the covariance over variance is the beta, and then the line would pass through the center of data. So that's why alpha hat will be equal to this one. Okay, I'm not going to go through all the detail because we discussed already. And this how the regression model look at the hotel price data is like this, right? So particular, the intercept is 133, the slope is 14, so which means that the city center should charge 133, right? For every mile away from the center, you have $14 less. So that is the interpretation. Okay, right? Because it's this, right? $14, right? So that is exactly the interpretation, right? Because this is the number in there. Okay, and this is the graph we plot, right? So ANOVA is this simply I have said this is SSE, right? And in regression, the good thing is you can relate SSE to in these kind of criteria. Okay, and turn out that these have a nice interpretation. You take the ratio of SSR over SST, right? Because if done regression model, the best model we have is Y bar, right? The sample mean, right? You learn that from estimation point of view, right? Sample mean is one of the best things you can do, right? And this the model that without X, right? This is what you predict, right? If you don't have X, right? The best thing to do is to do Y bar, right? If you look at hotel price data, right? If distance is not used, what is the model? Is the average price, hotel price in the city, is the best thing you can do the prediction, right? But now the distance, right? You build the model is the Y hat, right? So this is the part that you try to explain the change in price by distance to the city center, right? So this is the part that explained by model is SSR. And what you want to explain is this guy SST. The ratio between SSR and SST is how useful the data is, which is called R square. The reason why it's called R square is because it turned out to be, in this particular case, is the correlation coefficient square. So that's why it's called R square. Okay. Of course, this is only true when you have single variable, and to data multiple regression, we don't have. It's not easy to correlate it with this guy. So that's why we call big R square, but it has some meaning in this one variable regression. Okay. And the good thing is always between 0 to 1, right? When it's 1, it's perfect fit on the line. Okay. And the interpretation still holds true for multiple regression. Okay. Only this part doesn't hold when you have multiple regression. But the idea is same. It's like how much variation explained it by the. Okay. And as I mentioned to you just now, the SSE is the total sum of total squared error that the model failed to do, right? And usually we don't care about particularly this guy. Okay, we'll care about MSE. Okay, we divided by n minus 2, and probably some of you ask why is 2 not 1. There's a lot of reasons, but the main reason is because we estimate alpha and beta. We have 2 parameters to estimate, so that's why you would take away 2. So the denominator will be determined by how many parameters you have. Okay, so the more parameter you have, this guy will be larger. Okay? So that means that when you compare the model with different forms, say machine learning model, then this guy will be much larger, right? Because the denominator is like smaller, right? The more variable you have, right? The more parameter the model want to estimate, this denominator is smaller, right? Because the more you have, this guy is smaller, so it would be bigger. Okay, but later you'll see how we define that. But you compare different model, compare regression model to machine model, there will be you're using these 2. The main criteria, actually, you see the slides. These are the criteria that you compare. Why you sometimes use regression, sometimes you can use regression tree, sometimes you use random forest, and you focus on the mean square error. Okay, but so don't worry about it. But we talk about that. I mean, so but that will be the formula there. Okay, and you look at this hotel data, you can calculate all this number. That things shouldn't be an issue because it's the data is already there. And this slide, I think I omitted in the previous class, but which should be there because my slide is not updated, but now it's updated. So how can you do it from scratch? Okay, there's a formula you can calculate directly, but you can actually do the calculation, look at the mean of y, okay, and you can calculate the data minus the y bar, right? And this is double star is the rate square, right? And sum is sum of them. So this is exactly the formula we have just written down there, right? SST is just sum of the I minus y bar and square, right? This MP dot mean, right? And this is double star 2, okay? And SSR will be the predict minus star, right, square, and SSE is that one. And then you can do the calculation like this. I'm not going to show it, but you can try. The reason that we are not do that because I forgot to mention, if you run the regression, you thought R squared, it come out, it falls out directly. But actually, I mean, if you remember the regression, right, here is already there, right? So you don't it's right there already. So you don't have to need them, but it's there. But in case you really want to have when you fit the result, right, you want to get the R squared directly, that is the particular property you can get. Okay. So this is the slide that I didn't actually include it. For some reason I didn't update the slide, but now the slide is updated. Yeah. I mean, I'm sorry about that. I mean, so you can also calculate the root mean square. You take n minus 2 and take the square root. That would be the answer we care. And of course, you ask why we care about this. You want to care about this is based on the functional form. Or later you see when we remember we'll talk about log regression, then MSE is the thing we compare, right? Our MSE. Okay. So I think we talked about this as well last time, right? Then we talk about the data, whether I think I corrected the typo here, right? So we have this guy is a level, log. Then you probably ask in the example that given the book, right? And you notice that look at the hotel price and distance, and this one, the R square, the R square is, I didn't show here. It didn't show this one. So look at the 4 different model. I think we discussed that, right? And then look at the R square is when you take level, the R square is 1.5, 15% explained. When you take log and distance, log level, then it's 20%. When you take level log, it's 28%. When you take log, it's 34%. Okay, so it means that if you try to explain the percentage change in price to percentage in distance, that is the best fit of the model. So they're related in terms of the percentage change level, right? It's the best way to describe the data, right? So I think we actually talk about that, but just quickly go over again, right? If you do the graph, I shouldn't miss the graph here, but anyway, so these are all the explanation, and when you have log model, right, you change in beta means the percentage change in the price by beta. So I'm not going to repeat that. I mean, you can check it here over there. But so what did I actually stop is this guy, right? I talk about how to match this. Instead of allowing one line, you match them with segments, right? So you allow some kings goes on, right? It need not be a line. So at the end, we want to fit. We have a line here. We want to fit a regression here and a regression there. And you will ask why we do that, right? There's absolutely no reason why we do that, right? I mean, there's why sometimes cut off at that point. No particular reason. Sometimes this fit better, right? Just like you can imagine this is the idea that is behind is very similar to the bin scatter, right? You divide a group, you rely on the group before and after. I mean, there's 2 groups, right? The bin scatter will say, okay, this average will be my line, this is average, right? But here is like, okay, why don't I just fit regression here, and I fit regression here, and I have to make sure that they connect to each other. So then that is this linear spline is doing. right? It's very close to the bin scatter, right? But instead of a horizontal line, you fit a line so that they are connected to each other. Okay, and okay. So I guess we haven't looked at how to check the data, right? So let's look at the case study, okay, which is, I don't think we covered this last time. So this is the data. Where look at, I think the World Development Indicator, I think it's the United Nations. So data asks us is, okay, is it the case that people have more money and people live longer, right? And if you run the scatter plot, okay, which I didn't do it, turn out to be non-linear. The scatter plot looks like this guy. Okay, this scatter plot. So it looks like, yeah, it's like go up here, right? And some will go down, right? Because look at US, right? US has a lot of money, right? But their health condition is so worse, right? Look at what food they eat. I'm eating. That's terrible, right? So much sugar, right? And there may be some nonlinear, right? So we want to try to fit somewhere about this line. When you get very rich, then probably they don't live that long, right? So that is the ideal nonlinear. So that's why we want to fit them. Okay, fit this data. So again, this is a slide. You download this. Let's do it together. Let's go to the code lab and then we do it together and try to run this regression. Okay. So go to code lab. I think you able to do that here. And I need to sign in. Oh, I copied the code already. So which class I'm in? I guess I'm in IT class, right? Yeah. No. Yes, I'm in the IT class. And where's my code? Okay. So again, I guess up until now, you shouldn't have issue for copying this code and run in your. Okay. Let's run the code. Okay. Let's have this data being, oh, okay. For some reason, it's not copying the right away. Okay, so I have this guy there. Okay, and then after I download it, I probably try to check. Oh, got this guy there. So maybe instead of the head, I use the disk, right? What's wrong with that? Is there some issue? Let's see. Some problem with that. Let's see. Why is the case? Okay, I guess it's the problem is okay. Start the section.
The link is wrong.
The link is wrong. Let me see. Let me see here. There should be no problem. That should be right. This is actually. Oh, I forgot download. Okay. Okay, thank you. Oh, thanks for reminding me. I think I forgot the download button, so it doesn't work very well. But now I think it's okay. Thanks for telling me. We do have download for every time. I forgot. Is it the case? Let me go to it. We do have download for every data we have. Oh yeah, download. Okay. Okay, my mistake. So, oh, I have. Oh, just copy is not there. Okay. For some reason, I mean, stupid thing. So now, here is I use a what we call lambda function. Actually, we don't have to use that, but I want to do it because when you look at the textbook, they give you this function. You don't have to use that, but here what they're using is saying and say whether this, look at the year, which is 2011, sorry, 17. If you don't like this, I think we can use this will be the same. So I think we used to, the way we do, I think we used to say this. Right? I think the old way we do is we do say, I think we use this as well. Right? This is also the way we used to do. But if you, this is the same. Either use this or the book, the textbook, the code online, they use the lambda function. Either way we would do. The reason why I want to show it to you because you notice the textbook, the way they write the code is very different for each chapter. I think they hire RA, different RA do a different way. So even the same data set, they use very different way. So for no reason why they do that. But anyway, this is what they have. Okay. Maybe they use AI to do it. I actually not sure how they have that because the book is based on R and Python code is very not really well written. But anyway, so here they have another one they call MP log because I want to care about log. Right, log it, and this one I sort it for log so you can easily do the plotting. Okay, so I think I just copy and paste here. Hopefully, why is not working like this way? Let me figure out. That is rather stupid. I don't want to type. Let's see. Let's see if I have a smart way to copy and paste. Otherwise, that is not the edge. No, that's not smart enough. Let's see. Open this guy. Okay. Okay. Why don't allow me to copy? Okay. Let's type. Okay. fine. So this is unfortunately the type. So I just take the log, okay, and then I would have to sort them. Okay, I sort them up. Anything wrong with that? Oh, by. So yes. So this is the way we do, okay? And then what we're going to do is to cut off at 50, okay? And why do we do that? Because the graph look like that, right? Because you look at the scatter plot. They want to cut somewhere here. Okay. So, and you want to calculate log of the cutoff of 50 is here. It's around 4 because it's exponential. So X is here, and then you tell them create a basis, and then at a constant there you can run the thing. Okay. And this PAXI is to create this kind of basis spine. Okay. And for some reason, I hope I can copy. Otherwise, life is terrible. It's okay, not that bad. I can still manage. And two. Yes, it takes some time to create it. Now it's done, takes 7 seconds. Okay. And then we can run an ORS, because the same as ORS, because it just try to create a new basis. And let's run the regression. Syntax is wrong. Put the case on X, yes. What's wrong with that? I missed something there. Fit the model there. So you can see this the model, right? And probably don't care about how the coefficient, but at least if you try to look at this, the p-value are all less than 5%. So all these are good sign. And you can look at R square, although it's a spine, but it's still R square do still apply to tell you how good the fit is. Okay. You can explain now almost like 70%. Okay. And what remains is to show the data using the Matplotlib, right? So that is what I'm doing. Okay. Well, that's good. That is try to question my understanding of the code. Right, should be fine. Okay. Oh, I forget to bracket that. Sorry. That's why to come up this guy. So this is the code that you see from this one. So why 50 is like log 4, because it's trying to say it's more than GDP per capita more than 5,000, which is considered to be rich country, right? And turn out to be like this. Okay, so that's how this being used. I hope that kind of show you how you do the regression, right? So this is what we did, right? Log 50 below and above. This is the model we have. Okay, and the other way to do it is doing a square to capture the nonlinearity. So basically, is I do a regression, but I allow square there. Okay, and the only troublesome part is the interpretation of the betas, right? The coefficient is not very clear. What does that mean, right? Because before, if you don't have square term, beta 1 simply means x increased by 1, y expected increased by beta 1. But when you take the partial differentiation against this over x, then beta 1 is when you increase x by 1, y will be expected increase by beta 1, but also 2 times of beta 2 and times value of x, right? So it really depends on how x change to y depend on where you are, right? And they are related as well, okay? So in general, you have xn is also the same, so that would be the interpretation. But now let us do the regression, okay? So what we do is to create a square term, okay? That's called the power to 2, or you can use the star thing, okay? Up to you what you want to use. Say if I don't like the power, if I don't like the power, okay, if you don't like the power of 2, you can use 2. Okay, it should work. Okay. And the next one is I actually run the regression, and now I would use a new function, okay? We call the stat model based on formula, which we use all the time, okay? Because when you have more than one variable, which we do today, nonlinear multiple regression, we'll use the formula idea, okay? Which I will call data frame, and write the equation there, okay? Is the y equal to is a snail, and then you tell them what is the x squared. Immediately you fit it and you predict, you get the answer. So of course, you can combine, create a matrix and do it, which is the matrix algebra method, okay? Or you can do a more stat method, okay? So that is what we're going to do, okay? And this is more convenient, okay? This stat model using the regression square. So let's do it. Okay. I don't need that already, right? So I don't need that part. And run the regression, and based on y equal to this value of x, okay? And the data is the df, right? And I fit predict based on x. Oh, I don't think I need that part yet. Yeah. df there. So let me explain again this line, because while we often see this weird time many times, it's instead of giving me a y and x matrix, y vector x matrix, right? You will give a formula directly, and you code the data. And the Python is very smartly, they will take out the column that have this name, regress on these names there, okay? So that is a very convenient notation, because and we can check out what it looks like by running. Yes, I forgot to print summary of bracket. So you can see when I run this, right? The first thing to do is look at the coefficient, right? This is alpha, is 58. Beta 1 is this guy. Beta 2 is this guy, right? And the p-values, this one is okay, and this one is not so okay, right? So means then we will probably say this is not relevant, right? Because p-value is not less than 5%, right? And probably the nonlinear part is not very important, right? In the sense that actually, let me draw a diagram there. You will convince why what I said, the square term is not important. So suppose I actually plot them. I guess we plot the data, which you know how to, I don't need to explain this line, right? I import and I plot the scatter plot. I plot y predict. And this is the thing, right? When you try to plot them, okay, you will see this graph is, let me make it smaller. Okay, this I said non-linear, but you look at this line, is it very close to linear, right? Although it's a little bit curved, if you look carefully, I mean, use your eye a little bit, not straight, but the non-linearity is not that much, right? So actually, if you look at the regression result, there's no loss actually taking out this guy. You just fit the log is already, because log is already non-linear, right? So probably is okay already, right? So the question probably you would ask yourself is, okay, instead of this, should I do the another regression, which I didn't, I should do in this way, right? Rather that I should do the following. So I should call DF GDP PC, GDP per capita square, okay, 2P. I think you know what I'm doing. I use level square. Okay. And I try to fit this line, maybe regression 3. Okay. That I think will be a better fit. Okay. For this one, you can see the coefficient are there, is a better fit, right? And then you can also plot it again because I have the graph. I can also plot that. It look like this. Okay, you can see it's allow square term. I actually allow a non-linear line being plotted. Okay, although it's questionable whether it actually go down in this way, but that is the model predicts. Okay, and do note that we do have very little confidence about this part, right? Because of very few data. Well, later today, we'll talk about confidence interval and prediction interval. Then you see this is super big here if you want to predict, because there are few data over there. Okay, but I do hope that you can see what we're doing is like from the foundation of all this simple model, right? We have y and x, how long we live and how rich you are, right? And possible, right? When you're poor, you don't have enough food, right? You have more money, more food, right? And if you have a lot of money, then you go to drink beer, alcohol, party, right? Then that goes down, right? That is purely normal, right? Getting rich doesn't make you live longer, right? But that is what the data told us. Okay. So now at the end of the day, we conclude this chapter is which functional form we're going to use, right? And if you look at this one, okay, look at this one, I think you would agree that fitting a simple linear one is not the best, right? And whether you want the square is your choice, right? Whether which one is fit better, right? And if we purely wish to fit the model better, you should compare, say, R square or the RMSE, right? This kind of the data that you compare, then you would pick the model, which we'll talk about soon. But that would be the idea behind what we have done. So we've done the simple regression, 1y, 1x, right? And then we tell you different functional form. We take square, we take log. Okay, these are company employed technique, right? You can get cubic, right? Need not stop at square. So if you want, if you don't like this, actually, we can go to much more fun, right? Say, suppose I need not stop at square, right? We can go as far as we want to have fun, right? We can have, say, go up to, say, cubic 3, right? We can go to up to, okay, we can go up to there, okay, and fit the thing, okay, and do everything there, okay. This is data, okay. Still, you can see when you fit the cubic, this is still p-value is still there, so fitting cubic is not too crazy, okay. And the data looks like this, but then become more puzzling. Maybe a good fit, but how can we explain that? Right? It's like, okay, there's something goes up, but suddenly it goes down and go up again, right? It's not like roller coaster, but is there any theory behind, right? I mean, it fit very well, the data itself, but it has, I don't think you have prediction power. Actually, later you will see this is the basic problem of machine learning issue. You can fit the data better by adding more feature there, right? You can fit a very complicated functional form. But the problem is it going to hold in general? Because there are many features in data that actually is special to the data. If you try to generalize this, it may not be there. So there's a trade-off whether you fit the data better and the predictive power. So usually the regression turn out to be, most of the time actually works better than many complicated method. So that's why we still teach regression. So although you know that machine learning is very tempting to use, but regression still actually, in many cases, is actually better than a lot of models. Okay. Unfortunately, this is a very surprising result. I mean, you would expect if you would use sophisticated method, then you would be able to be picking better. No, not the case, right? I mean, you can understand this, right? Look at these days, right? And there are so many new stuff comes out, right? New product comes out, right? But at the end of the day, right, flower remain one of the most useful gift to give girls or boys, right? Handbag, right? KTV, right? Still, I mean, being the most useful tools, right? Between boys and girls, right? And right, you don't need a very fancy thing to work out, right? Simple, maybe the best. But anyway, that's what I say about this chapter, right? So we learn basic regression, and we know different transformation of the X can also be done. That means that I allow ourselves to do nonlinear way, right? It's like this way, or even any crazy form that you can imagine, right? And do look that if you try to use this model, you should have some good idea why up and down in this way. Otherwise, I would not use this. I would have a linear one. I mean, or even log one that is more capable to explain, right? The log one is easier to explain, right? Just percentage change in the GDP and then change in the life expectancy may be easy to pick rather than have this one. If you don't have a good story, telling you this model, probably you have a trouble to convince the manager, right? I would rather take if you ask me what model to take, I'm not going to take this one. Probably I would take this guy, or even just the log one will be this one will be also fine. So you can see even simple regression, I mean, can go very far. Okay. And let's let's have a break, and after the break, we go to the next set of slide. We go to lesson 5. The idea is to generalize this, okay? And first, we want to talk about how to use the model, right? So far, we just guess the model, right? But you don't tell you how we use the model, right? The model is predicting X and Y, right? How we use X to predict Y and explain Y will be there, okay? It's because this model is just a line. How accurate is this? Is we go to the confidence level, and we go to all the texts, just the p-value we set already, and we get to the multiple regression, okay? So let's have a break of 15 minutes, and then we come back at 15:33. And in the meantime, if you have time, you're welcome to fill in the you reply, but otherwise take a rest. We'll resume at 15:33. 但是应该不会考虑，很简单。甘蔗水，甘蔗水，甘蔗水。你看你那个一是也在，一是对，对那个考试上面。怎么可以来讲？所以我在那个年纪的时候，他会对啊，非常对，非常好。我也用在白纸上，每个月我不想管。对。但它不仅仅是一样，这个是跟你的是在处理数据的时候啊，data 处理可能不行，combine 这个重要，去找进去 combine 这个什么，这个不是正常人就可以想得出来这些的。我的朋友就是非常多成人地方的一个迷的一个，我看到本来是我写的本子，我说哎，我傲气的，我看不懂他写的。这种东西都很一样。都是能干的。对，看一个，都比使用大部分。都是比如说这个分东西啊，多东西的放在这里，变得
那怎么好？
当然，空间比较好，我们空间第二排是第三，然后可以给我们站一百。不仅不是看的，比如说我有写3个人，我们3个人拿到了不要讲，第一头，关系第二、第三，地区，一个人。这就比较实用的。不行的是，跟我的那个，很多东西技巧我觉得是，连是不是有我都不知道，技巧我觉得有。有同学说这个东西 x 跟 y 什么关系？通常我不知道。对对对，除非这个东西 x 和 y 是很有多少事情可以，要不然其实我是正确也是把这个意思不同的。兴趣，我觉得，然后我觉得喜欢的，现在地理的，因为我是两个方面的，最大的都会在哪？
哦，对对对。对对对对对，还有这些电路图的。但是我要有时间做，导入以后。我现在做这个，现在做这个实验，要不要我们就在这里分嘛？真的行，分为一群，然后一个先放英国打完，就跟那个米萨要有嘛，不要嘛。黑人都不是，黑人都不是。我这里跟对，但是我做的是。所以，但是如果你是我看过很简单，反正我是看到做 DID， 反正我是看到这个 DID 是做，对，你花点时间，就是记得可以简单的。好做的时候，遇到过什么？我都没有遇到过，有那种 DID 上有些城市，对，费城特别大，就感觉啊，对，我感觉差别蛮大的，差别真蛮大的，就是真的是那个城市跟那个跟小地方感觉工作好像到。对，小的那工作肯定不太干。我手法，好手法，写作完了吗？我觉得我在那里，但我没有在国内力气。我在美国说，在美国说一下可以吧？在国内讲。这里我觉得但是女生比较怎么说，极端一点，就太喜欢了。我觉得一般人，就是我一般其实我做的可能都是在美国就想回国，我在国内就没有。我记得我那时候在跟他。我来过那个地方，我一个朋友蛮厉害，一个毕业以后也那个其实是相当于是那个是 branding， 就特别大的确实也是。我父母都想。你说他们学生比较少，你说这大部分你在深圳哪里做？你在我应该我都挺喜欢。我是福建的，但是我哦，没有，他们是这样，他们说肉很肉，对肉，对防护也还好，这个有那个最主要就是肉很搞笑，但我嗯，都会比较的。
So let's see how are the response. I guess what does that mean? Happy or sad? Looks like Java face. It's Java face, I guess. Yes, you're right. I mean, I use Chrome to open the file. Maybe you're right. I should use the Chrome to open the file. That possibly solve the problem. But I don't know why it's not allow me to open the file for some special reason. I think they make it a default file can. There's some way to. I don't know how to do it. But anyway, let's see. No, none. Oh, thanks. Well, just some story. Short story. Long story short is I take my son because his hair is very long, so I take him to a Japanese quick cut Japanese quick cut hair store, right? Like a QB house, right? It's like very quick cut, and then the hairdresser asked me whether I want to do it as well. I said, okay, just do it together, and then just and they said it's father and son style, 夫子装. So that's how I do it. Final request. I mean exam, right? My exam request. I think you're asking what is in the exam, right? Or what might be in exam, right? That is, I guess that's what it means, right? I'm not sure what it means, but I guess what you ask is what is the scope of what type of the question I may ask in the exam. Suppose it's like this. If not, then you just leave the comment again. So what is the exam? What the style will be? Okay. Will be, I think what I'm trying to ask is like, let me check if I have last year sample questions. If not, I upload let me check. Do I have that? No, I can check sorry. So the last year question, then last year sample question, then you see what I'm asking in general. Then you have some idea. So last year is like this. I mean, I'll upload the real last year paper that I'm trying to do. So one of the things like I probably now understand what's going on now, right? Suppose I have that model, I have X and Y, right? And this is the Python code, right? And I'm asking, given you this, just explain what it is, what's the model, what's the coefficient. We'll talk this immediately. What's the coefficient? What are they? So don't worry, I put that on the. You don't have to pick. I'll put that on. So don't worry about that. This is sample like this, or this is a regression tree. That's like this, and how you can do it. Okay. And this is the sample question of last year. So I put a real last year final there, then you will take a look. But that would be, I think would be, you understand what I'm asking. So there will be some of the Python code there, this Python output there. I ask you how you can use it, right? So very practical thing. So I hope that would make sense. Okay. Did I answer the question? I hope I answered the question. If not, then you can ask me again. For some reason, I exited you reply. What happened? Sorry for that. Yeah, I think I will put the report. You can see it. I guess it's the case. If I didn't answer a question, please leave the message again, or we can do it in the second break. Okay, so far so good. Just to let you know, today is Wednesday. Make no. It's raining. Okay. Surprising. NumPy. Yes. So yeah, simple regression or just regression actually can be better than machine learning. That's actually one of the things that we have to warn you, because you don't have to use a very complicated tool. Sometimes simple tool works better, right? And yes, this is the formula that actually we will do all the time when we have multiple regression. It's SML OLS and then formula Y X X X X. This is the formula. That's very important. Yes, as a business, I mean, telling good story is very important, especially if you run particular type of regression and you show different shape and you need a good story. Otherwise, I mean, why I believe there's some highly nonlinear relation, right? Squared in the regression, yes, this is what we do. Yeah, I think everyone well. This means laugh. Okay. Maybe your mouth is O. Okay, the speed is okay. I'm doing all right. Overall, okay. I think it's fine. Thank you. Oh, maybe younger. Okay. How much it cost? I told you it's a QB house, so it's just like $70. Why did why did I do? Because I took my son there. My son is very long, so I have to do it. So that's the reason. And no particular reason. Okay. Thank you. I mean, I'm surprising this year people are interested in my hairstyle, interested in my t-shirt color compared to last year, but it's okay. I try to change a little bit to improve, make you pay more attention. Now, I think we can continue. So lesson 5, okay. And as I said, we have estimate model, but we didn't tell you how to use it, right? Because we just have a model and tell you that we can look at the p-value, the coefficient, and check if they're okay. But we haven't really teach you how to use the model directly. So we will do construction of confidence interval, okay, and precision interval, and this where we use the model, how we use the model, and then we will go into break into more general. Instead of x and y, we will use x to explain y. We will use x1, x2, x3 up to xn to explain y. So that is a more general thing. But in terms of the Python code, it's very simple, right? But there's something complication we have to discuss a little bit. But overall, shouldn't be a big issue here, okay? And how can we because we run a regression, right? So regression is simply saying that we collapse the data into a simple model and with bunch of numbers, right? With regression, we just end up with alpha and beta, right? So the question would be, okay, is it enough, right? Then we need to know more, okay? The question is like the following, okay? It's like we mentioned confidence interval before, right? It's like instead of estimate point, we estimate range of points, okay? So that means that we can have confidence interval for, sorry, there's no I here. No I, sorry, there's a typo. So it should be interval for alpha head and beta head, right? The interval is how big is the slope, right? And how big is alpha, right? Because beta itself usually have some meaning, right? Remember the hotel price scenario. We explain distance by price by distance, right? That means that if the level model, the beta means that we go away from 1 mile, then the price drop by such, right? That is our mean prediction. But we probably want, besides the point estimate, we want an interval estimate, right? This is when we care about that, right? And if you estimate in economics, one of the regression that run most of the time is what we call the earning equation, which said X is year of education, Y is income. Why you care? Because why you're here, to be honest, right? I mean, maybe some of you would be interested in ITM, SM itself, right? But I guess most of you, I mean, maybe I'm wrong, but you care about after graduate earn more money, right? So if that's true, then that regression would be the most meaningful, right? One more year, you spend large sum of money on the master program, you want your job opportunity, you earn more, right? So the beta is the return of education, right? Because if you have a regression, right, about your money, year of education, right? Okay. And if you look at data, usually it will look like this kind of style. Okay, something like that. Okay. And like this. Okay. So this is primary school, this is secondary school, this is college. Okay, and this master. And if you try to plot, then something like this would happen. Okay, so probably go down a little bit. Okay. So if you finish primary school, then you get higher, then secondary school go higher. Master degree, you get more. PhD like me drop. So for some reason, well, it's a self-selection. But anyway, but that would be something like that happen. So the slope itself will measure how good, how valuable the return of education is, right? So that's why most of people study master and that's it, right? Because you study further, actually your money will drop, right? So, but that would be like this, and then this will, the slope by itself you will care, right? But probably you also care about the exact value, right? Suppose I tell you, right, a particular education level, right? You want to tell me what is his return, right? But you also want to tell me how good is this estimate, that you give me a confidence level, right? That is the idea, right? You don't give me 1 point, but you give me a range of points, right? That is the CI there. And there's slightly complication in regression. We have to distinguish what's the CI and PI, okay? And CI is estimate on the average value, right? and PI is particular value. Okay, and the main difference is like this, right? If I give you the CI for master program, what does that mean? It means I have group of master students. Okay, I want to care about the average earning. Then what you get is the CI. If I care about a particular guy, that is master program, the earning will PI. So that is the individual will be PI. The group then will be the CI. So that would be the difference. But that would be the difference. Prediction level and confidence level. And I will do some hypothesis testing. So that would be the main thing we're doing for the first half of this section. So don't worry, we will go into the detail. Okay. So if you recall how we do interval, it's just plus minus 2 standard error, right? And the formula, okay, turn out to be very simple, like this. Okay, I don't think you need to. If you know math, you can easily derive that, and we are not going to talk about that. Okay. But one thing I want to mention a little bit is we are just not very careful in explaining is what regression is doing is the following. We actually are assuming the data is generating in this format. Okay. When run regression, what is assumption behind when run regression? Is saying that underlying X and Y are related in a linear way with a error term. Okay, so let me draw a diagram to explain what actually I'm doing, because this is a little bit subtle, and probably you have to understand this part. So what does that mean is the following. So when run regression, implicitly, this is assumption we have. Sorry. It's the following. So there is a true alpha and true beta we never observe. Okay. There is a line here. Okay. The slope is beta. That's alpha. Okay. What we observe is not exactly this line. Okay. Why? Because in this world there can be things that affect Y rather than X. Okay. There's a random element there that is something we didn't model. It's called epsilon. Okay. And what we observe is in the world is there's some variation here, right? Depends on how well you're doing. And this epsilon, if normal, then we look like this, right? Right? If you have, right? If you fix this number here, called x2, right? Called x1, right? If you x1, right? If where x1, then the value can be generated like this, right? The most likely is in the middle, right? So it's a bell curve over there, right? Fix my x, and then this will realize in this way, right? So it's a bunch of bell curve, but they stack in this dimension, right? You can imagine the 3D shape, there's x and y, but there's a curve over there. Okay, and what we get is sometimes you get here, sometimes you get here, but most likely it's the middle. But it ended up here, right? So that's why the data at the end you got is somewhere here, 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 here. This is what data, right? If there's no this term, then everything on the straight line, right? But in the real world, what you observe is some kind of things that you can't observe, or some random element there that lead to multiple paths. Okay, and if you make the assumption that the shape different x has the same shape, okay, the variance same, that is called homoscedasticity. Okay, and this is the real restrictive form. It's classical model will assume that. Okay, but we will assume usually heteroscedasticity, which means that we don't have to assume this will happen. It can be the case that when you get larger, the variance can be very large. When it's small, variance can be very small, or a particular value can be very small, right? Maybe like this can happen, right? So can be the variance can different across different value of x, okay? Unless you assume they're same, which is very special. The formula you have is very special, okay? But we don't have to make that assumption, right? So that is why it's called robust, okay? If you don't use data, if you don't use Python, if you ever know data, that is called regress yx robust. If you ever, for everyone who knows data, right? If you, this is the regret yx, all right? And if you do economics, then probably this is very familiar to you, right? If you never do economics, you don't do data, then you, this looks like a alien language to you. But for Python, that is not something very difficult to do, so don't worry. So that is what we're going to do. So you will see I have NumPy as that model API, I have x and y, I add a constant to x, I run regression. The only new thing is I have the covariance type. You can use HC1 or HC3. That will correct the problem. Okay. Then you print it out, the result the same. Okay. You will see the same outcome, but the only difference is this value will be, this value is different. This value will be a little bit different. And in general, always recommend you have to use HC3 or HC1, depends on what you like, the correction. But this is the way you should do. I mean, if you know data, every time people ask you to do robust. Okay, so that would be the thing we do. Let's copy. Hopefully, I don't need to type again. Oh my God, I was kicked out from the code lab. At least I don't have to sign in again. I think we're in chapter what? Which chapter I mean? Chapter 9 already. Okay, that's fine. Then it's just asking me to debug my code. Should I? Maybe your computer don't have this problem, but it's okay. We can fix things. Is there any issue? Oh, this is small letter, sorry. Okay, so that's how I get the answer. Okay. So, I mean, I changed the number here, sorry. Just probably different from there. Maybe I should get back to. So that means that if 2, then the p-value is 1, so basically it's rubbish, right? So this model is useless, right? So if I change it 10, say, then this model, although it's more than 5%, but at least somewhat useful, but still, it's still a rubbish model, right? But just to tell you that how you can do it, and then you can see the note here. They use the XC3, tell you, right? As I said, if you look at the textbook, the code they will use XC1. That would be something similar. I think HC3 is the one that used in this data as well. If I remember correctly, HC3 is the one. Okay. Okay. So this is the model we have here. Okay. I think we did talk about this a lot of time, right? How to test this hypothesis of beta is 0 or not. Look at the t-value, right? We already mentioned many times is look at the guy there, right? So we just simply look at this p-value, right? And in particular, look at this x1. And in this case, this model is crap. So just basically just forget about this model, okay? And you can do the same for the alpha, the intercept. Of course, the intercept is, the model is very complicated. Even this is more complicated. But don't worry, we are IT manager, right? We don't care that, right? Just look at the result and then we're done, right? So we don't really worry about that. The p-values here, again, you drop it, right? You can't reject, right? So it means that we have to keep this idea that alpha and beta are 0, right? So this model is essentially useless. Okay? Is that okay? So now we go to a data. I hope that the case study help us to see what's going on. So this is the earning data, and I guess in the US they're obsessed with the gender gap. Okay, and what they want to look at the government data and try to see if the man and the woman are making different earning. Okay, and one of the main problem, okay, of this is later you will see we have to be very careful about the data itself. First, we have to restrict to age, right? And we include the employed people, right? And exclude self-employment. Okay, so that is the restrict. And we need to look at normalized by number of hours, because in general, men work more than women, because women would work less for 2 reasons. One is they may got pregnant, right? Then they work less, right? Or second, they may take care of household more. Then that is also one of the reasons why work less. So that's why I have to do it, right? This is the data, work more, then you want to look at hourly wage, right? And if you look at some statistics, you notice that men would actually earn 17% more. Okay, so that is what we want to look at. So this is raw data. Okay, you look at mean. On average, men earn $24 per hour, US dollar, and women earn $20. Okay, and the gap is 70%. Okay, and you can do this median, right? 90% quartile and 25% quartile, right? Is women uniformly earn less. Okay. So what we're going to do is look at data. Okay, it's the employment data we're going to do. Okay, CPS data. So let's download this data. Okay, and then we will run a regression together and check every single thing is going to be follow what we want to do. Okay, I think it's good that it's not there. Then you will check out your syntax is right or wrong. So we download data. Okay, from the things, and as we do, usually we would want to look at the general data, how it looks like, right? Say, look how the data looks like, right? And if you want the head, or you can do the describe, look at the summary statistic, right? Describe and see what we have there, right? So 23 columns, right? And these are our wage, earning per week, many race, ethnic, age, sex, with a child, so on and so forth. Okay. So now the next step is to look at this, is to look at a variable, okay? We want to look at man or woman, right? So we define, look at data sex is defined as 1 or 2. The data, you look at check the data, right? The most important gender gap is the sex. The sex here is either 1 or 2, right? If you want, we can look at the value count, right? This is something like something you want to do. Sex call value counts, okay? With some summary statistics. You will see almost half of them are men, half of them are women, okay? And then 1 is man, 2 is woman, okay? So that's why we want to have a variable set as a dummy variable for female, which is when it's 1, then it's female. 0, that is male. Okay. So that's what we're going to do. Okay. That's the first step. This rather standard thing we do is, okay, why with a bracket here? Because once a bracket, this become a logical statement. It's 0 or 1. Right. So that's will become that. Then you can try to look at this. Again, you check it out. It become 0 or 1. So it's true and false, right? True and false becomes actually 0 and 1. If you learn, you're an IT manager, you should know it, right? The Boolean type is 0 and 1. Okay. And the next thing is, I want to look at the wage, but we want to normalize by hour. So it's earning per week divided by earning the hour of work per week is the wage we care. And then we want to group by man or female, look at their hourly wages. Okay, so that is what I'm doing here. Sorry that for some reason that the code is, I need some time to type, but group by I think describe. So you can see that depend on your female, true or false, right? If your mean is like man is 23 and female is 20, right? And then the rest with the SD, the max is all there, right? Or the max is a little bit crazy because someone is making almost 3,000 per hour. I don't know who is it, maybe lawyer who is making 1,000 US dollar. I don't know who's making such a money, but and that seems to be too good to be true. But anyway, right? Because that is too crazy. But anyway, so this data. Now, as we said that actually we look at this is not sufficient because it's possible that the wage difference due to the choice of the job, right? Because usually men tend to choose a more crazy job, more risky job, right, than women, right, in general, right? So, or men choose some job that is more high paying, right? Say computer science, right? That's doesn't seems to be the true case here, right? ITSM, we have more female than male, right? For our program, right? Maybe marketing, right, is more men than women, but that's the old day. But now I think in general, in the college, we have more female than male. Unfortunately, I mean, with the fortune, I don't know, but that is what happened. So what we're going to do is to fix our occupation first, Okay, look at all men and women in particular industry. Okay, then avoid the problem of choosing the job. Okay, and we run the what I'm doing. This will be female. So this will be female. Typo. This will be not. I'm not running wage over wage. Sorry, this is female. Okay. I look at. Sorry, I use the mouse to write this. Maybe I should write better, right? Maybe I should type it out, right? I mean, okay. So this is supposed to be there. Okay. I will run the wage over female. Okay, I use the log version. You don't need to use log, but log may make more sense. Fit better. Okay, it's non-linear. Okay, and use the robust standard error. So that is what we are doing. So let us go to the data. Okay, first I look at the log wages. I do the NP NumP log the hourly wages. Okay, and then I want to focus on computer science. Okay, and turn out to be is the occupation number is between this 1005 and 124. Don't ask me how, but this is how what the data tells you. Okay. So this is you filter data now. Okay, I focus on particular group of data. Look at the CS. All right. Is it some error? Let's see. Let me check if there's some error. Oh yeah, it should be this guy. Sorry. So this is the CS will be the group of the data that I only take out the computer science. Okay. Maybe I just do one step if it looks better. Like this one icon. Right? As long as it's belong to this one, then it's considered the data. Okay. So if you try to make sure this is okay, then you just try to do the data again, right? To see whether actually we did something right. So let's try to look at this. Okay. No, CS. Okay, so actually we cut the data, right, from more than 100,000 to like 5,000 data point, right? And you can see more male than female, okay, already, because computer science, right, you have more male than female in the early days. Now I think it's similar, okay? And what we're going to do is to use this regression, right? As I said, we regress the wage over the female, right? Let's see what would happen. And I use the robust regression XC3. Okay. This is the formula. Here you can see I just do once and for all, feed the data and immediately run it. Okay, I think you can. Given your Python knowledge, I don't think that would be difficult, right? So I include that. And I have that one. XC3. Okay. And maybe I want to print the summary instead of summary. That looks better. So this is our model. Okay. So although the R square is very pity, right? It's only 1% of data, but we do see the p-value is small enough to be meaningful, right? It means that whether it's female or not actually would change, right? Turn out to be, if you're female, you actually is like 14% less, right? Because that is what the log wage means, right? Being a female, you get 15% less, okay? That is the model. Hourly wage is 15 less, okay? So this is the point estimate, right? We want to look at also what is the interval, right? So look at the CI, right? It's between 11% to 18%, right? So in the US case, it's being a female, then you earn 11% less or 18% less when you go to job market as a female, right? That is what happened in the data, right, in the US, okay? I guess now it's reversed in US. Probably you are a woman, you get more. That is, this is now what I think the data is, but I didn't do anything, so I didn't know, okay? But anyway, this is gender gap because this doesn't contain zero, right? So we reject the hypothesis that the gender gap is due to the occupational choice, right? Because we already fix high-paying job like computer science, right? And turn out that women are earning less in terms of hourly wage, right? You cannot claim that it's because of women are pregnant and they work less, right? So now we look at the other thing is look at, it's computer science? Yes. This is marketing, so there's typo. This is not company, it's marketing, okay? Look at marketing occupation, and we look at this occupation number is 735, and I call it marketing, okay? So we do the same, but where am I? Focus on marketing again, okay? Then let's run the regression with the marketing. Okay. And I have this 735. Am I right? Yes. And again, once you run that, probably you should check whether your data, how it looks like, right? By looking at MKT. Okay, let's see if, okay, already you can see now we have more female than male in marketing. And the wages, they're different, right? Not too much, but you still see there's some difference, right? You want to see whether there's actually the difference going on. And surprisingly, actually, men that in the lower range, men earn more. At upper range, women earn more, right? So potentially maybe very attractive women earn a lot. Handsome man doesn't help a lot, right? But ugly men may be earning a better, right? They're not so attractive women. But anyway, that is what the data tell me, but I don't know. Okay. And again, run the regression, right? The same thing, but the data is MKT here. Okay. So let me copy this and run again, and then you will see what we have. Okay. Sorry that there's a problem with the data that don't allow me to do it quickly. But that's fine. Again, I want to use a print summary instead of summary. That because look nicer. Okay. And again, you will see that a woman actually learn 11% less, but the p-value is not 5%, right? So in this particular case, we'll say men and women are same with equality of earning in marketing, right? There's no difference in men and women, okay? Because the p-value is 6%. So there is no wage gap. But in this case, is computer science actually men earn more than women. Okay. Is that clear what we have done? So this is the case, and you can see the confidence interval is including 0, so you can't really reject the idea actually 0. Okay. And well, probably you want to say, can we do more? Yes, you need more data, right? Because now it's not conclusive, but you might think that actually, right, 11% on average should be there, right? And then probably you want more data to see if this conclude. So that is how you would proceed analysis like this. Okay. And next is with the Stark laser package to produce a professional looking table, right? So if you're not here last time, that is the pipe install, right? It's a standard thing you do Python, right? You install it. Okay. This is how, because the Stark laser is not in the standard Python distribution, you have to use this to install that. And once you did that, then you just copy and paste here. And then, well, missing so much. I really don't want to type. Okay. Let's see if I can copy that instead. Okay. No. Okay. Just type. So it means that here what it means is I want to reverse order. I don't care about intercept. I care about female or male first, reverse order. And I would want to rename it as intercept as a constant. So because I really don't like the term intercept. Okay. Here I have to give dictionary. Okay. It's a dictionary. Then I will output the table. Why is complaining to me? Yeah, no problem. Okay. What's wrong with that? I don't know why, but maybe the reason. Maybe the reason is because I used the statement here. Maybe I changed the M.Phil where. That should work. Because true and false may not be the best thing to say. I changed to, oh, what am I doing? Oh my God, it's running everything again. But it's to work out at the end. So let's wait after the break. But that at the end, we end up in this table. Okay. And this table can summarize what the model gives you, right? And that tells you that in the computer science, this is 15%. And for the marketing, it's like on the mean is 11%. Okay. So usually we use P as 5% as standard. And if your data is large, use 1%. Okay. So for IT manager, I think use 1% is more appropriate because you do have a lot of data. Okay. And So let me quick. So I should have break. I shouldn't stretch on. But other break, we talk about how to use the model, right? Because the line only gives us the mean estimate. We want to have a confidence interval for the prediction. Okay, there's a equation there, and then we can use the looks very complicated thing to generate this kind of graph. Okay, these are the graph later you will see. This is the red one is our point estimate, and the curved one is what we are predicting. Okay, the closer to the data center is more accurate. The further away, we have less confidence. Okay, so it's not a parallel line. It's a, I don't know, a U shape there. So the more data you have, then you have more confidence. Okay, but let's do it after the break. Okay, in the meantime, I'll probably put up another survey so that you can try to answer if you have time. But let's have a break of 15 minutes, and then we will resume at according to this clock, it will be 16:40. Oh, sorry. So you can tell me how well you're doing. Is it going to be too fast or too slow? I don't know. Maybe too slow, I guess. I should go faster. Relax me.
我去装水吗？没有。
点到一个，可以的。点到一个东西，不是谁的？
见到是谁出出来拿的？
啊，对，肯定不是我的，因为我没有这个东西，没有什么高级的东西，
不是有线的，我的
都是啊，都是
有线的比较好玩。
有些很快两个不想搞，搞有些的快的几率比较低，能多充电。闪有线的不会丢，不容易丢。
So we have MP where then it works. Right. So let's see how we're doing. Okay. I think you can use the printer, but I guess they charge. Oh, that's I never use that. I don't know, but I think that's the case. Yes, robust standard error. Yeah, that's very important. Speed. Okay. I think overall is fine. I think yes. In the US data, maybe you're a different type of gender, then you earn more, right? 等于在中国少数民族加分，对吧？Same thing，少数就可以，you get a minority bonus. Same goes on here. So very quickly we finish this part, and then we go to the other one because this is I think it's rather simple, but there will be some more stuff we need to go over the code. Okay. So quickly is with the line, right? This is the line we have, right? And the line actually gives us the best guess of the model, right? But usually we are not just interested in the mean value, but rather the interval, because that the data we got is just a random realization of what might happen, right? So that's why you would want to look at 95% CI, right? Plus 2 minus 2 SE, right? That is standard way. And if you follow the simple one, this is the formula you can use. The complicated one will be even more complicated, right? But I guess that should be fine. So this is the model we have seen, right? This data I try to predict at a constant there, and this goes on, right? I'm not going to explain this code again, but I just copy and go over here. What I need is the next set of slide, right? I think that is very annoying. Missing one number 9. I hope your computer don't have this problem. But oh, I don't have actually fit this one. So this is the regression. Okay. And here is what we're going to do. It's slightly more complicated. Okay. So what I'm going to do is I want to plot the line. Okay. And I plot the way I do is I use NumPy linear space. What I'm doing is look at x smallest value, biggest value. I cut into 100 data point there because I want to draw a line. And a constant, and this become my new x. Okay. And use the regression result, I get a prediction. Okay. And the predicted result, look at the mean value, is the y prediction. Okay. And I want to look at the confidence interval, that's the dot interval, okay, the prediction value. And it's CI, so it's false. I use 95%. Okay. If I change it true, it's the PI, which we'll talk about soon, but this is the model. And this is lower and upper. So it's below is minus 2 SE, this is plus 2 SE. Okay. So that is the idea. But let me copy it and I explain line by line again, because I think that is a very important code that you need to know. Okay. So I have a new function called linear space. Okay. Is to create a list of number that start from the mean, smallest mean and biggest number, right? And I do 100 data point there. Okay. And that is the first line. And this line is adding constant there, become a capital X. And I, based on the regression result, I fit in this X value, I give me the Y. Okay. So, and then I get the predict value of Y. Okay. And this is 1. 0 and 1. So let me explain again what I'm doing. Let me run the code first. observation equal to false, alpha 0.05. So let me explain the code again, what I'm doing. Okay. So what actually I'm doing is, right, I have a data, okay, and some more data there. Python actually, based on the previous code we generate, is run, we have a line, right, run a line. So what the first line told me that is, I do the following. I pick up the minimum x. Okay. This is x mean, x dot mean. I pick up this point. This is x max dot max, right? And here I need to collect 100 data point here because I want to plot. Okay, you can actually 2 is sufficient, but anyway, I pick 100 because maybe non-linear, right? I want to pick more. And I add a constant there, right? Because it's a number, I add a constant, right? And I use this line to generate 100 data point here. Okay, what I'm doing is, okay, you feed 100 data point. Okay, this would feed this line, give me this one here, right? Somewhere here, right? Predict all this result, and this is Y predict, right? So list of numbers, and based on this prediction, I want to draw confidence interval, right? I will draw 100 of them, right? For each one, I will draw a what's upper bound, lower bound, upper bound, lower bound, upper bound, lower bound with 100 point of them. Okay. So each value of x, I will have an interval, right? Because each x I have Y predict, and Y predict I tell you the interval there, right? And I put in 95% interval. You can change it to any number you like. Okay. And once I have that, now I'm ready to do the plotting. So what I'm doing here is I would have a scatter plot based on origin x, y. I plot a line based on x and y there. Color is red. There's a line. And now I want to fill between this interval, right? Fill the color gray, the lower bound, upper bound, right? Fill between this area. I call it constant interval. And then I label them. This other thing are very natural, right? So that's how I thought all this. I hope you would be able to explain what's going on, right? I don't know why it's like this. That's a bit annoying. It's lucky that it's not too crazy. Okay, so it should. So this gives us a table we have, right? So if you put a copy, there should be something very simple, right? So this is, if you give me the value 4, this is the interval I would guess, right? So that would be the model you would get, right? Instead of this, you get this. So this actually is not very surprised. This is something actually you see a lot of time, right? If you try to look at the Python graph, from forecast. And actually they have the same, right? They would have, this is the mean and this is interval. So no different. And of course, their model much more complicated, but this is actually what it is. 95% confidence. I think 95, right? If I look correctly. They didn't say, but usually it's 95%, and then they will tell you where they are. Right? The further away, you're much bigger. Right? So that's the same idea. The closer to the mean, then it's where well, but further it's a bit more difficult. Okay. So here is continue the idea that you would look at the earning data, right? Here they look at is how wages are affected by your age, which is experience, right? It's possible that we didn't explain, but we want to see how experience changes according to age, right? It's the wage profile, right? So you look at the model, right? You try to look at wage over the age, right? That is rather simple. We can just look at the data. This is something we have done. Okay, so just don't worry about it. Right. I don't know why we have. And I want to print the summary. Maybe I have version 4 because I think I used up the 3. Maybe I should flip 5 because I think I used 3 before. So this is the regression result. Okay, you can see that as you become older, your wage goes up by 1%, 1.3% each year, right? Because log on the left-hand side, so means that every year you got pay rise for 1%, 1.3%, right? That's US data, the hourly wage. Okay. Right, so that is the model you have, right? And this is the model we look at already. So, and then you can look at the CR interval, right? And look at the mean, okay? And okay, this is how we do it. Do we need to actually do it? Maybe to save time, I don't copy, but I just tell you what's going on, right? So how to do CI here is I can use another way to do it is get prediction. Okay. And then dot summary frame, put the alpha there, then you will give you the mean, median CI, and median upper and lower. Okay. The same as what we see. Okay. Once you did that, I join back to the original data. Okay. So that gives me all the data I need to predict. Okay. I don't want to spend time copying, but you can try to check it out. And then once you combine the data, okay, you would want to, when you plot, you want to focus on the data that the wages is within this range, middle range, and you sort them up, you can plot. Okay. And then you saw this X, this is Y, this is predict, this is lower upper, the same as what we have seen. And you plot the line, it looks like this one. It's a curve here. Okay, so this is the model you estimate. And because of data variation, you should expect this is the real model, right? The much thicker. Okay. This is the best case scenario. This is the worst case scenario. Okay. Is that okay? I'm not, because of the time, I don't want to do the copy because I have to figure out why I can't really copy. And for the PI, the same, okay? And the only difference is the PI is individual, not the average. Okay? So the difference is instead of SC called SPE. Okay, I don't know why the book called it this way, but the difference is just this one more, has one more compared to the earlier model. But I don't think we really need to worry about this because we're not statistician, right? So we just know there's a formula there, and then you just run the Python, then we're done. Okay, the same equation, the Python will just the same, but the observation CI rather than mean CI. Okay, so this gives you the lower and upper. Okay, and you do the same code here, scatter plot, fill between gray, fill between yellow, the PI, right? And then if you see this, is pretty amazing because the mean value is like very narrow, but the individual value will be much thicker, right? So it varies, right? On average, maybe you get older, actually, they increase the wages. But if you are not so lucky, then you can end up like here. Right? Lucky you are going to be there, right? So it really, things can be different for everyone, right? Because there are lots of variation over there, right? So that is what we have. So finally, it's like, is our regression model actually work beyond the data? That is very important because we summarize Y and X, right? And we want to know how they're related, right? And of course, the interval like this tell us, okay, how age is related to earning, but is it going to generalizable? Because this is past data, it's going to be true or not, right? Because in old days, people older actually earn more, right? But now we know if you're beyond 35, then you're unemployed, right? Right, 30, right? And you 996 for 10 years, and you get fired, right? You beyond 40, then maybe an issue, right? So I don't know. It really depends, right? So have to be very careful. Okay. So I hope that I skip the copying the code. You can try it at home. If you have any issue, that let me know. But there shouldn't be any issue there. So 10, I talk about multiple regression. Okay, now we are actually entering into probably the part that we talk about real model. Okay, this is the model actually we will be using, and this is the one that actually you will use for your projects and thing before. Up until now, it's just like toy, and now this thing we use in production. Okay, and I can safely say that many people actually do this and for a living. Okay, just run regression. Okay, and that's what we've seen here. Okay, and what we do is instead of using one Y, we have bunch of X. Okay, based on bunch of X, we want to see how to explain, and then there's no difference. It's just like minimizing the vertical distance. Okay? It's not a line, but it's a plane. Right? Imagine x1, y, x1, x2, and y is vertical. Right? You fit a plane there to make sure that it's y. Just like if you imagine, now use your imagination, it's a good time. So this x1, this is x2. Suppose 3-dimensional y here, right? There's a point here. You try to fit a plane to make sure the vertical distance to the plane is the minimum. I hope you can imagine. Okay, this is a good one. So this is the data is like here. You try to fit a plane to make sure the distance between, so this is here, this data here, 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 here. So you can try to fit a plane, right? So that's the idea. Okay, so vertical distance. I hope it makes sense to you. Okay, So in matrix notation, this is a vector of x, it's a vector of beta, and there's you multiply, you get y, and then the solution looks like this crazy formula. If you know matrix algebra, it makes sense. If you don't, that doesn't make sense. But it doesn't matter. You just know there's some solution to that. But whatever, we don't really care because we have Python, right? So, and this the formula with the standard error for the coefficient will follow something, again, a crazy equation, which you and I doesn't care anyway, but I just put it there in case you read the book. There's a formula you can derive, okay? But this formula do tell us something important I would like to emphasize on, okay? And that is something will be important as well, is, okay? If look at the standard error, means how accurate your coefficient is. Depends on many bunch of stuff, which we don't care that much. But here, the square root of the denominator is something we care a little bit, okay? Is the RK square. What's that? RK square is you regress xk on all the other x. So suppose R1 square means you regress x1 on x2, 3, 4, 5, 6, 7. Okay? Maybe make it easier. So if you have considered regression like this, y equal to alpha plus beta x plus gamma z, say, 3 variable. Okay? And what is r square x? Okay? You actually run the regression alpha, beta, z. Okay? And look at the r square of this. Okay? That actually is somewhat you can imagine is in this two variable world. This r square is just correlation coefficient between x and z, right? Two variable. The r square is exactly correlation coefficient, right? And if they're close to 1, that means that this error is infinite, right? The reason being that if these are so similar, right, then you can't distinguish which is which, right? So you can't tell whether what's the effect, right? For example, the following question. Suppose a man is going to send a red rose to his lover, okay? And every time he's going to send the red rose, then you are not sure whether the girl like red color stuff or rose by itself, right? If what you have is always a red rose, they're so similar, right? So it's not clear that what actually she likes, right? So you have to distinguish. So have to be the thing cannot be so similar. If you include this x and z are so similar, then your standard error will be very big. And you can't, because you can't distinguish them, right? That means that suppose you try to, as an IT manager, right? You have access to the user data, right? Maybe they are highly correlated because say you have how much time he spent on the website, how much click he did there, right? And maybe there's how much scrolling he used. There are many things you can capture from the data, right? And if you put the regression, you put something so similar there, then your regressor will not be coefficient. Then it will not be significant, right? So have to be a little bit more careful when you do the t-test, okay? At that time, you have to do the f-test instead of t. but that is way beyond the scope of our class. But that is something that you have to be concerned of. Okay. So that is the idea like here, right? So if I look at the earning data, I have female, I have age, right? I can explain wage different by male gender gap and also age gap, right? So we can see already there are two things together, right? So I want to include them in the same equation, right? The wage gap can be, the wage difference in your data can be due to whether the individual is female or male or how old they are, right? So let me look at this, okay? And in this particular model, we want to further filter the data, make sure that people work more than 20 hours per week and actually make the earning and look at they are always at least college level, okay? And we run the regression. I think data we have already. I don't need this code, okay? And this already have already. I don't need that again. Okay. And this is the one I need. Is I look at this filtering. Okay. Let me do this filtering quickly. This thing's hate me for some reason. It's working. A cop bracket to make sure everything all right. This empty space. Okay, so that is working. And now we can finally run a regression model. Okay. So what we do is we will run the model, explain the wages by gender, and we run the wage against female and age, and we try to run age and female. Okay. So you can see by this formula is very convenient because we can run any regression as we want just by running. Oh. Okay, so it's running there. Then what we need is to look at Stark laser and comes out the answer, but I'm not going to waste your time on that. But this is the result. Okay. So first, I want to interpret this, and this is probably the end of our class. And you can see, at least in this particular data, women earn 20% less, right? Because log wages, percentage. Okay. And here is the interesting part is at the age, actually doesn't go away that much, right? From 19% to 18%. So age is not the reason why this is there. Okay. And why I want this regression, okay? The reason is being that these numbers are related, okay? And this is in the literature because you forget the age, which is important, That is called omit variable bias, OVB. And if you look at, this is what it means. There's a math behind all this, but I don't think I have time to cover that. But simply said is I have two regression equation. This is correct, this is wrong because I omit them. So the question is how beta 1 and beta are related. And if you run another regression, Z on X, okay, turn out to be this coefficient, they are related in this way. Okay. And the reason being that this is positive, right? This is smaller, right? Because the age effect for female is negative, right? So on average, age and female are inversely related. Okay, so that's why female are younger and older people actually earn more, right? So that's why when we control the age, okay, that actually gets smaller because the effect compared to this is negative, right? Because age, right, you older you get more, right? And in this model, you forget about age, right? But they're younger, right? So when you include age there, that will actually become less, right? Because you consider age, right? Because female are younger. And you say older people earn more. So that is the reason why it's here. It's okay if you don't fully get it, because I put it here because the book could put it here. And for our purpose, we don't have to worry about those because in most cases, you don't have to interpret the coefficient, right? What I ask you is, okay, we remember for our course is you know how to write this formula, this regression, right? We'll be expected to say, I give you the regression result, you how to interpret, and I give you the columns, you know how to run the regression. I mean, that will be, you will see the assignment. Just one final thing I want to ask before we end today. Is it the assignment one too easy or too difficult? Who think it's too easy, raise your hand. Who think it's too difficult, raise your hand. If no, then I haven't made assignment 2. So if you think it's appropriate level, I will make something similar. If you haven't, I mean, I haven't made it because last year is more, I asked out. So this time I just, if you think it's okay, then I will make the same level. Okay, the assignment is not there until we finish this chapter. So will not be there yet, but let me know if this is too easy or too difficult. I will just make adjustment accordingly. Okay, so I hope at least now you know how to run multiple regression, right? And how to export that. You can try them out. So I guess I shall end here. If any question, feel free to ask me, and I'll stay behind to answer the question you might have. Enjoy the weekend. I'll see you next week.